You have some additional definitions in this chapter. One extension is that you could have a complex random processes when the real part and imaginary part are two random processes. Or you could, similar to what we have done in previous chapter, you could define vector random processes, and there entries of them, there are multiple random processes. Correlation of x and y, if they are complex, you put a conjugate on second one. We write the vector random process with capital bold. Obviously, if you put t1 and t2 and these two are same, so you take a sample from time t1, sample at time t2, so you get x of t, and if they're complex, you get x of t, you put a conjugate, and this is equal to x of t to the power of 2. However, if you forget to put these t2, it's not going to be equal to that, and this will become x of t to the power of 2, and this will not be a real number. And sometimes its expected value may even be 0, which is the case for like Gaussian circular symmetric random process. So if you put the conjugate, this function will have very interesting properties in lots of applications. The autocorrelation function is a positive definite function if you have any complex random process. The positive definite function means that for any arbitrary n, if you take any number of samples, let's say this is t1, t2, t3, they don't need to be in order, and let's say this is tn. If you take arbitrary, and n is arbitrary for all n and for all times, all tp. And then if you choose arbitrary complex numbers, AP is a complex number, and if you put it there, always this guy is not only a real number, but also is non-negative. The proof of this is very easy, because what you can do, you can define a random variable a1 x of t1 plus a2 x of t2. Once you define your arbitrary time instances and arbitrary values, and then say an x of tn, okay, and define this random variable z, and say the z magnitude to the power of 2, which is z conjugate. This is a real number, and its expected value should be also real number and should be non-negative. And then the expected value of this one is going to be exactly equal to this. So the proof is very easy and straightforward. Okay. So another example, if I consider a line spectral signal, which is summation of some sinusoidal, so in frequency domain, you put at frequency omega 1, omega 2, omega 3, they don't know, and let's say etc. And let's say this is omega n, and then you put a magnitude here, magnitude of a1, etc. And then you have these waveform, random waveform, because AI are random. Assume that the expected value of AI is 0, and these AIs are uncorrelated. That means that the dot product of this one is 0. So this is delta. So delta I comma k means equals 0 if I is not equal to k, and it's 1 if I is equal to 1. So that means that they may have different variances. So in this example, the autocorrelation function of x of t can be calculated easily. So I have to write expected value of this x of t at t1 and expected value of x of at time t2. I put a conjugate. This is a summation, so I get a double sum. So it becomes expected value of summation over I of AI e to the power j omega I t. For the second summation, I have to write summation, but I cannot use the same dummy variable. So I use, let's say, k, and then ak e to the power of j omega kt, and then I conjugate on it. So this conjugate will go on the top of AI and also makes these minus. And then you have a double sum, multiply them together and simplify it. So if you simplify it, you'll get this expression. So what you see in this expression, if you have these conditions, if the expected value of AI is 0, and if AIs are uncorrelated. Zero mean uncorrelated complex magnitude. So this is called complex magnitude. And this is a waveform which has different line spectra. In that case, this autocorrelation function, interestingly, is only a function of the time difference, T1 minus T2. And this is very interesting.